So, good morning. Well, we already talked quite a bit about the synthesis problem yesterday. So the difference between verification and synthesis, of course, is that we don't consider the implementation to be the input, but rather the output of the problem. So we start with a specification, and ideally we produce an implementation that satisfies the specification. Actually, there's a decision problem here, which is the realizability question, which asks if there exists an implementation for the given specification. And then there is the actual constructive problem of building such an implementation, if one exists. All right, so the focus here is on reactive systems in line with the other talks, meaning that we're looking at systems that continuously interact with their environment, and the correctness of these systems is characterized in terms of a temporal formula or perhaps an automaton or a device like that. There is, of course, a hot research area concerning the synthesis of sequential, data-intensive programs. So I will not have time to go into this, but of course, this is exciting too, and they're interesting connections, in particular if you know about syntax-guided synthesis. This is closely related, but I won't be able to get into that. So we're looking at systems with a finite state space. The focus is on control, not on data transformation. And typical examples for such systems are the reactive layer in embedded systems and hardware, right? So let me start with a few examples of this nature. So this is a toy example from the lab. It's a little search and rescue mission. So here's a robot that got stuck because it's broken. And here's his little friend who tries to rescue him and bring him back to safety. And what you see is that this robot sees its environment through very limited sensors. So they are short-range sensors that help him avoid bumping into walls and the likes. And then there are long-range sensors that, for example, help him identify the victim robot. So the search robot needs to find the victim and then go to it. And once it's there, it docks with little magnets and then brings him back to safety. So another little example of this nature is this. So here we have two robots that do something really nice. They clean up your desk, except that they do it in a way that your kids might do it. Now it's a nice little example because there are two robots interacting. And actually, the main challenge is to avoid them to push each other from the table. Now, the fundamental premise here is that it's easier to say what you want to do rather than how you're going to do it. So, in a slightly simplified fashion, what we want to say is that eventually all garbage should be cleared from the table, and the robots should never push each other from the table. And you don't have to worry about how to analyze all the sensor data and how to react to that in a step-by-step fashion. Now, a little bit more grown-up example. This is Alice, an autonomous car built at Caltech. So they originally built this for the DARPA Urban Challenge. So that means you have an autonomous car that navigates an urban environment with cross-traffic and intersections and all that. And you need a traffic planner that decides, for example, whether you should stay in your lane in which you're traveling, or if you should have a passing maneuver, if you should stop at an intersection, or whether it's safe to reverse, for example, in a parking kind of situation, and so forth.
Just excuse me 1 second. Please clear the seats for human beings rather than
All right. So Alice was originally built in an ad hoc manner. That was back in 2007 when they participated in that DARPA challenge. But what they did later on was use it as a test bed for all sorts of verification and synthesis techniques. So the specification here consists of traffic rules. Basic examples are you shouldn't collide, you should obey speed limits, and also goals such as reaching a certain checkpoint on the map. So that was the DARPA challenge, that you had these checkpoints on a map, and you needed to plot your course to reach all of them. So I think it's worth pointing out, and we had this discussion yesterday after Francesco's talk, that obviously you can't just write an LTL formula and voila, there's your autonomous car, but rather in this case the traffic control is part of a hierarchical control stack. So in this example with Alice, what we're talking about is the traffic planner. So this is concerned with should I stop or go at an intersection and so forth. And it interacts with the mission planner above it. So the mission planner says, these are the checkpoints I need to get to, for example, in this order. And below is a continuous control problem. So in this case, you have a path planner and follower. So this means that you set target points in 2D space and then monitor as your car drives in two-dimensional continuous space, and you correct for deviations from that path, right? So at the reactive level, we're not concerned with this continuous control problem, but rather we set goals for the path planner. And below that is the actual actuation interface, which then interacts with the vehicle. And at this level, we handle, for example, emergency overrides and that sort of thing. And there is a basic consistency check if the commands that you're issuing to the car are going to blow up the car, and that sort of thing. So that nicely isolates the problem where we can be useful. Another class of applications is hardware synthesis. And just to give you a flavor, the AMBA bus benchmark is probably the best known benchmark from this category. So the AMBA bus is an on-chip communication bus that connects cores with memory or direct memory access controllers and so forth. It's actually a pretty involved protocol. You have up to 16 masters and 16 slaves. So the communication is driven by the masters, but it's a pipelined kind of protocol. So you can have one master transferring data, and in parallel some other master setting up the address it wants to send to, and yet another one just sending in a request for the bus, right? So the way this is done is that there's a list of guarantees specified in LTL that are taken from the standard, the protocol standard. So these are things like when a locked unspecified length burst starts, new access does not start until the current master releases the bus. And these guarantees are supported by assumptions, right? Because what we're actually synthesizing is the arbiter circuit, and the clients to the protocol are the external environment. So if we specify, for example, that the bus is fair, and every master who wants the bus will eventually get the bus, this couldn't be realized unless you had an assumption that says that whoever has the bus will eventually give up the bus, right? So these guarantees are matched by assumptions. For example, that the clients indicate infinitely often that they have finished processing their data, and they do that with some signal, in this case by lowering h-ready, right? So what you do is you have a fairly short specification along the lines of 15 LTL formulas.
I'm curious about this assumption, rather than to say that if the client lowers H ready, then something should happen, rather than why assume that the client does it infinitely often. The client may decide to go to sleep. Why make this assumption?
Well, you need the assumption for multiple clients, right? So it may be that you're a fifth in line to get the bus, and then you need this assumption for all the four clients that, or in this case, masters that are ahead of you in line. So if you would put that into the guarantee, then that would be a lengthy formula because you would need to state all this. So the idea here is that you have this list of assumptions, and these are sort of global assumptions that you can use for whatever guarantee you're trying to realize.
No, but it means that, for example, suppose that one client dies.
Right.
Now this assumption is violated, and now anything can happen. And this is very unrobust, right? One
this is true.
may just die.
This is true. So
this is a very strong assumption, and it makes the system very unrobust.
okay, so let me repeat Moshe's comment. I learned that yesterday. So Moshe's comment is that this is a really dumb way of specifying systems because you have this long list of assumptions, and if any of the assumptions break for some reason, then your guarantee is nil and nada, right? Because if the assumptions are wrong, then you have specified your, then you have satisfied your specification without doing anything. And this is, of course, true. So in this example, we assume that nothing breaks. If you want to be robust, and people are discussing this, of course, then you would want to work with minimal assumptions for every specific guarantee, or maybe have a notion of robustness that says that if I'm actually using fewer assumptions, then this is more robust than if I'm using more assumptions and the like. But this is a level of refinement that we won't get into here. Okay. So let me state the reactive synthesis problem, which, as we discussed yesterday, actually is one of the oldest problems we have in computer science. It goes back to Alonzo Church in 1957. So the basic idea is that we have a requirement phi on the input-output behavior of a circuit, and we compute a circuit that actually satisfies this requirement. So you have your component that you want to build, and your input consists of an infinite sequence of signals. Your output, again, is an infinite sequence of signals, and this requirement phi is a relation over these inputs and outputs, and what you're looking for is a circuit that guarantees that this relationship actually holds. Now, there's also the game theoretic formulation of the problem, which means that you consider the environment which produces your input as one player, and the system that reacts to that input as another player. And of course, the goal of the system is so that to respond in a way such that the resulting sequence of inputs and outputs satisfies the specification. The goal of the environment is to prohibit the system from achieving this goal. So the way you play the synthesis game is that your player 0 produces outputs, player 1 produces inputs. You play the game over an infinite number of rounds, and in each round, player 1 first produces an input, then player 0 produces an output, and if the resulting sequence satisfies phi, then player 0 wins. So let's do this in a really simple example. Let's say we're building an arbiter circuit. So in this case, we have two clients that produce requests for a critical resource, and we want to build a system that decides who gets access to the critical resource at every point. So we have as input the requests R1, R2. So these are just Boolean signals. They can be true or false in every step. And the grants G1 and G2 mean that, well, client 1 and client 2 respectively gets access to the critical resource. Now, the specification might be a conjunction of two simple properties. Mutual exclusion. We don't want to give the same resource to two clients, right? So it can't be that at some point in time both G1 and G2 are set to true. And at the same time, we want the arbiter to be useful. So every request Ri from some client I should eventually be followed by grant GI. So obviously there is a winning strategy to this. So initially, before we have a request, we would not issue any grant. Now, when there is a request, say if the input is R1, right, then we might respond with grant 1. So we set G1 to true. If there's a request R2, we might respond by setting a grant, giving a grant to the second client, so setting G2 to true. Now, if the input is R1, R2, so there are requests to both from both clients at the same time, then things get slightly more interesting. So we might do something like this. So this is again, we start by outputting no grant at all. If we see R1, then we output just G1. But if we see R1, R2, then we go into this mode where we alternate between G1 and G2 until we have served both requests. So what's interesting about this is that at this point we need a little bit of memory. We need to remember that there is an outstanding request. And there might, of course, be simpler strategies to realize all that. So for example, I could just alternate the grant between the two clients, no matter if they have requested a grant or not, right? But in particular, this would be a winning strategy for my game. Yes?
Does it make sense to add another specification which would say that basically it could be the case that a system makes a request 5 times and it's granted only once. Does it make sense to ensure that every request is followed by a grant? Specifically 5 requests are granted and 5 grants.
I see. So the question is, in this example, a request, a request might be on for a number of steps, and then there is one grant, and that sort of satisfies all these requests once and for all. Would it make sense to just count the number of requests and then make sure that, there's a matching number of grants? So it does make sense. Obviously, this is not a regular property, so it would not fall into the class that you could, for example, describe in LTL. And of course, this is a synchronous setting, so it could be done. We could actually count the number of steps that the request was held. But generally, you would not want to do that, to have this dependence on the counter, right? So the way this kind of circuit works is that once you set the flag, that means there is an open request, and you actually keep it up until that request is satisfied. But of course, there are situations where you would want to go beyond regular properties. Okay. So at this point, let me just give you the gist of things. So the problem that we're trying to solve here is really hard. So synthesis from LTL specifications is doubly exponential. So I think Moshe's line on this is that exponential is the new polynomial. So this is not so bad, really. But still, this is something to worry about. And what we saw yesterday in the Pnelli-Rosner paper is that if you generalize the problem to the distributed setting, then it becomes undecidable. So you might really want to do that, and that is a limiting factor, and we'll see how bad that really is. Now, in the last 10 years, there has really been amazing progress on this. So roughly, I would say that there are 3 phases of work on the problem. The first phase was following, Church's original formulation of the problem, which led to the basic game theory, the Büchi-Landweber results that the resulting games can actually be solved. Rabin's correspondence to tree automata. So the fundamentals were solved early on in the 60s. In the 80s, there was the second phase where the whole problem was again investigated from the perspective of efficient logics like LTL. But what we see in the last 10 years is that there is the transition to practice happening. And the reason I'm saying that is that there's a growing number of tools that actually solve the synthesis problem. Despite this complexity, we're still far from the level that, say, verification has reached, but there are tools and there is a growing number of applications. And of course, this is driven by a process where we're finding specification languages that have better performance, and we have new techniques like bounded synthesis. And you can see that this engineering aspect to it becomes more prominent also in things like the synthesis competition. So since a few years back, there's an annual competition at CAF that started out very basic, but more and more benchmarks are being collected. So now there are around 3,500 benchmarks, which is still far from where we want to be, right? Because many of these benchmarks are actually instances of families of benchmarks. But still, it means that there's a transition going on where you can start treating the problem in a more empiric way, right? So we can, for example, compare different logical encodings based on actual benchmarks that you haven't invented yourself, right? They may not be perfect, but at least there is a growing number where you can see if things work. So this is roughly where we're at. What I want to do in my series of lectures is start. Yes, please. Oh, I'm sorry. There was a question.
Maybe, please. You have a question and you see that the guy is not listening. Just
Yeah.
speak up and
Just
say-
shout if I forget to look at you. So, please.
Okay, so what do you mean that synthesis is 2x time hard? What is the decision problem?
Okay. The question is, what do we actually mean by this? What problem is 2x time hard? So the problem is, given an LTL specification, does there exist a finite state implementation that satisfies the LTL formula?
So it is satisfiability.
Realizability, yes. So the difference between satisfiability and realizability is that since LTL is a linear time logic, its models, well, actually, this is the discussion that Arne drove yesterday, but traditionally speaking, it's a sequence of labels, right? Now, what we're looking here in realizability is not a sequence, but rather a implementation which reacts to which reacts to inputs by producing outputs. So you could consider this a tree, or maybe a mealy machine, Moore machine, something of that sort. And I expect that not only there exists one sequence that satisfies the LTL formula, but actually all the sequences that can be produced by giving inputs to that system need to be correct. So this is what we're talking about. Very good. So as I said, we'll start by looking at the fundamental games. These are classic algorithms to solve these infinite games over finite graphs. Then in the second part, we'll get back to the logics and see how different logics actually define different games that can then be solved by the classic algorithms. So you could see this second part as the quest for the right language for synthesis, because obviously how difficult it is to solve the synthesis problem depends on the compactness and the expressiveness of the specification language. And I think that the final word is still out what the perfect specification language might be here, if the questions are the same as for verification or not. So we'll look into that. And then in the third part, we'll look at the bounded synthesis approach. So the idea here is that the search space for implementations, of course, is huge. So if you have a choice, you might want to prefer simpler solutions over more complicated solutions. And this has two benefits. One, that you actually reduce your search space. And the other benefit, of course, that you might get simpler, better understandable, and so forth the quest here is actually to find structurally simple implementations and what might it mean to find a simpler solution. So an obvious idea is to limit the number of states that you need in your solution, but there are also other parameters such as the number of cycles. And then in the last part, I'll get back to the distributed synthesis issue related but extending the Rosner setting. Okay. So let's talk about infinite games played over finite graphs. I know that quite a few of you are experts on this topic, so I apologize if this is boring to you. But I want to start with the fundamentals and see that, I mean, the beauty of this really is that these games can be solved algorithmically, so you have a solid foundation to actually solve the synthesis problem. So we're talking about a finite game arena. So this is a finite set of states, and a subset of the states are owned by player 0. A subset is owned by player 1. So I'll indicate that with circles for player 0, which usually is us, right? And with boxes for player 1, the opponent. Then there's an edge relation that connects these states, and we require that the game can continue all the time. So there's always at least one outgoing edge. This is just to make sure that these infinitary winning conditions make sense, right? So that we don't get stuck with just a finite play. Now, a play is an infinite path through the arena. A strategy for one of the players, so a strategy for player I in the arena is a function that maps a finite history, that is a finite sequence of states that ends in a state owned by a player I and maps this history to a successor state, right? So the strategy needs to be such that it can actually be carried out. So if you have a prefix of a play and you apply your strategy, then you need to get an actual successor according to the edge relation in the arena. And we say that a play is consistent with a strategy, well, if your play actually applies conforms to the strategy whenever possible. So whenever it's player I's turn, the successor must be chosen according to the strategy. Now, there are various special types of strategies. A positional strategy or memoryless strategy only depends on the last state. So that means that rather than talking about the entire history, it suffices to talk about the last state. And actually, in these very simple games that we're going to talk about, reachability, Büchi, and parity, there exist positional strategies, so that's fine. A generalization of this would be finite state strategies, where you can realize this strategy with a finite state machine. Now, we're going to look at 3 winning conditions in the following. The first one is reachability. So a reachability game consists of an arena and a set of states that we want to reach. So a play is won by player 0 if the play actually visits this set of states at least once. If that doesn't happen, then player 1 wins. Now, Büchi games have, as you would expect, again a set of states, and player 0 wins if that set of states is visited infinitely often. If it doesn't happen, then player 1 wins. And parity games are again a generalization where you have a coloring function. The coloring function maps every state to a natural number, and player 0 wins a play if the highest color that is seen infinitely often is even, otherwise player 1 wins. Right? So in the end, parity games are what we want. You might encounter, of course, say Büchi conditions that you want something to happen infinitely often, the dual of a Büchi game would be a co-Büchi game, that you want something to only happen finitely often. And of course, if you can solve a Büchi game, then you can solve a co-Büchi game by solving for player one, right? Because the objective of player one is to prevent the Büchi condition from being satisfied. So one straightforward motivation for going beyond Büchi games is that often you have specifications that have an assumption and a guarantee. So you say, if this happens infinitely often, then that happens infinitely often. If you're just looking at the guarantee, then you have a Büchi condition, right? Something needs to happen infinitely often. If you just look at the assumption, then you have a co-Büchi condition. If you manage to make the assumption wrong, that is, this happens only finitely often, then you have a correct implementation. But really, you don't want to solve for the Büchi or the co-Büchi part in isolation, but rather you want to say either the assumption is violated or the guarantee is satisfied, and that would bring you out of either Büchi or co-Büchi games. So you could do that in a parity game, where you label the states where your guarantee is satisfied, say with color 2, and the states where the assumption is satisfied with color 1 and everything else with color 0. So then if you satisfy your guarantee infinitely often, then you get color 2 infinitely often, so you satisfy the parity condition. But if that doesn't happen, then you want the assumption to be satisfied only finitely often. So you don't want to have that the states colored 1 with color 1 are visited infinitely often, and the ones with color 2 are not visited infinitely often. So this is again captured by the parity condition, because if neither of them are visited infinitely often, then, well, your highest color that appears infinitely often is 0, which is again even, right? But we'll get more into this. So we say a strategy is winning if is winning from some state if all plays that are consistent with the strategy and that start in V are won by the player. The winning region is the set of states from which that player has a winning strategy. And we say that the game is determined if the winning region of player 0 combined with the winning region of player 1 actually gives you the full arena. And it turns out all the games we're looking at are determined, and this makes it so convenient. When we have the winning region for one of the two players, then we also have the winning region for the other player. Right? So when we say we want to solve the game, that means we want to determine the winning regions and the winning, at least for one of the players, we want to have the winning region and the winning strategy. So let's start with reachability games. So in a reachability game, we have that player 0 wins a play if the play visits a given set of states at least once. So in this example, I have V4 and V5 as the states I would like to visit. Now, if I happen to start my play in one of those two states, then player 0 has already won, right? Because we have already visited the goal, and it really doesn't matter what happens after that. But there's more. So for example, V3 and V8. So these are not states that are directly in my set R, but they are still part of the winning region of player 0. And why is that? Well, the states are owned by player 0, and there is an edge that leads into the states that I have already identified as winning. Therefore, of course, I just need to play into these states, and I can show that I win from those states. Now, the same holds for V7, right? V7 has an edge to V8. V6 is an interesting case because it's owned by the other player. But if I look at that state, I see that the other player doesn't really have a choice because there's only one edge that leads into a state that I already classified as winning. So this is also a winning situation because in the next step I will be in a state that I have already classified as winning. So the general picture is that I extend my set of, I extend my winning region always by states that are owned by me and where I have an edge into the states that I know to be winning, or that are owned by the opponent and where all edges happen to lead into my winning region. So more formally, this is a fixed point construction. So I start with the goal state with my set R. So this is the attractor set construction, and the zeroth approximation of the attractor is this set of states. And from there on, I increase the set of states step by step in just the manner we did just now by reasoning one step backward and adding these predecessor states whenever appropriate. So the n plus first attractor consists of the states that were already identified, so the nth attractor, and the controllable predecessor of the nth attractor. So the controllable predecessor implements this idea that either I have an edge into the set or my opponent doesn't have an edge that would not lead into it. So we go through all the states owned by me that have a successor state according to the edge relation that is in the set of goal states. So note this R can be now any set, right? Not just the set of goal states here, but like, for example, the nth attractor here. So either I have the state is owned by me and there's an edge that leads into this goal set, or the state is owned by the opponent, and for all successor states, that is for all states where that start from V with an edge in E, well, the target state is in R. And then I built the least fixed point on that construction, and that gives me the winning region for the reachability game. So the winning region for player 0 is the least fixed point of this construction, and the winning region of the opponent is simply everything else, right? I take the full set of states and subtract the winning region of player 0. Now, the winning strategy for player 0 in this game is called the attractor strategy. So it simply means I want to get as close as I can in every step towards the target, meaning that I move to the nth attractor such that the n is as small as possible, right? So I might, from V6, for example, which is the state that we added in the last step, so it's in the highest attractor, we would, well, sorry, this is owned by the opposing player, so I don't have to say what the strategy does for this one, but V7 we added in the step before that, and we would play to V8. From V8, then we would play to V5, and V5 was in the 0th attractor because it's a goal state already, right? So the way the fixed point was constructed immediately gives us a strategy how to accomplish our goal. Of course, if we're outside the winning region, then this is not possible because we actually don't have a successor. If the state is owned by us, that would be in the winning region. So in that case, our strategy can do whatever it wants. It won't be winning anyhow. Okay. Now, conversely, the strategy for player 1 is simply to avoid getting into the attractor. So the winning strategy for player 1 just chooses a successor state that is outside the attractor for player 0. So, for example, if you're up here, then you don't want to play to v3 because from v3 player 0 would have a winning strategy. Instead, you stay up here. Likewise, from v2, you stay up here rather than playing down into v5 where player 0 would win, right? So if the game starts up here, then it will actually stay up here according to this winning strategy for player 1 rather than at any point going down to the winning region of player 0. Okay. Now, in Büchi games, the objective is to visit the given set of states infinitely often. If that happens, then player 0 wins, otherwise player 1 wins. So in this example, we have v4 and v6 as our target set of states. Now the problem now is a little bit more complicated than in the reachability game because it doesn't suffice to get into the set once. You actually have to make sure that you can come back, right? You need to be in the set F infinitely often. And that means that some of the states in F may actually be traps. That is, you feel good that you got into them once, but then you don't have a chance to come back and you actually lose the game. So the main task here is to figure out which of the states in F are actually good ones, right, where you can come back. So if you look at this example, then v4 would be such a trap. It's in F, but the opponent can play to v0, and then you're again stuck up here, and you have no way of getting back to the lower part to v4 or v6. So you should really ignore v4 in your set of target states. You should play to v6 instead, because if you happen to get to v6, then well, your opponent may play to v7, but you can play back to v6 and therefore reach F infinitely often. So we again have a fixed point construction for this. And this time we start with F, so the set of Büchi states, but we reduce them step by step until we don't have any of these traps anymore. So the zero approximation is the full set F. And then so essentially the zero approximation means that we can at least come back 0 times, right? So we'll increase the index, of course, and ultimately we can come back infinitely often. But initially, the only guarantee is that we can come back at least 0 times. Now, here we switch perspective and say, okay, let's take this set and even the attractor of it. So these are then the states where player 0 can reach a state that can come back at least n times. So these are from the perspective of player 0, but then we take the complement. So the complement contains all states where player 0 cannot even ensure that we can come back n times. So that means that actually player 1 can ensure that we visit at most n times. So if player 1 can ensure that we visit at most n times, then this is good for player 1, because since there is a limit on how often we can visit F, we don't have a chance to visit infinitely often. So now what we do is we take this set of states and remove it from our recurse set. So since these are states where we can only visit at most n times, we actually take the controllable predecessor from the perspective of player 1 of this set and therefore get the states that are in F where we can at least come back n+1 times. So we have increased the index here by 1, going from the guarantee that we can come back n times to the guarantee that we can come back at least n+1 times. And now we take the greatest fixed point of this. So all the states that are left after I have done this, as long as it takes to get to a fixed point, are the states where I can actually come back infinitely often. So now with this subset of F, the recurse set, all I need to do is use an attractor strategy to play into this set of states and then continue by coming back infinitely often. So this is the winning region for player 0, and again the winning region for player 1 is simply the complement of that. All right. Let's take a look. The winning strategy for player 0 always moves to, as close as possible to the recurse set. So in our example, we identified that the recurse set is actually V6, right? V4 was not good, so we removed it. So the fixed point will only contain V6. And then we have an attractor strategy that takes us back to V6. So, for example, from V7, we take the edge that leads us to V6. Likewise, from V3, we have the edge that takes us to V6. But if we are somewhere else, like up here, then it really doesn't matter what we do, because the opponent can keep us outside the attractor of the recurse set. So we won't win the game anyhow, so we might as well do whatever we want. Okay. The winning strategy for player 1 tries to limit the number of times we can come back to the set of accepting states. So if we are in a state where the guarantee is that we can visit, that player 0 can enforce at most n return visits to F, then we try to move to a state where the guarantee is that player 0 can enforce at most n-1 visits back to F. If this is not possible, then we simply stay in a state that still has the guarantee that there are at most n visits back to F. Right? So if we happen to be in V4, for example, which is a visit to the accepting states, then there is one visit to the accepting states. Then we move to a state where there are 0 further visits to the accepting states, and from there on we stay in states where there are no further return visits to the accepting states. Obviously, yes.
So they say that move from a state in W1n to W1 -1. So there might be many possible states that one can choose, right? So there are different. There are a set of winning strategies for player 1 to choose. So those winning strategies, how can we determine which one is better than the other from a synthesis point of view? Since different winning strategy might lead to different synthesis results, right?
Okay, excellent question. So the observation is that I just say move to some state in Wn-1, and that of course might not be a unique choice, because I might have a number of successors in Wn-1. So first of all, this construction is a little bit non-deterministic the way I have stated it, because any of these states would do, right? So you can pick one that you like. Now, the second part of your question was, can we exploit this somehow? Because one strategy might be better in some way than another strategy. So certainly we could heuristically exploit that. For example, if we want to minimize the number of states explored or so. But keep in mind, of course, that this algorithm doesn't have a guarantee that it would recognize all winning strategies, right? It's just one particular set of strategies that are being defined by this construction. So by no means would we get would we have a guarantee to get an optimal solution if we did that. But still, heuristically, we could of course exploit the non-determinism in this. All right. Okay. Yeah. So this brings us to parity games. As I said, we do have to go beyond Miller games, because otherwise we couldn't capture many specifications that we're interested in. Of course, there are many winning conditions that have that property that they're sufficiently general. The major reason that parity games are so popular is that they do have positional winning strategies. So, yes, please.
Just a comment continuing on this.
Ah.
This would give you at least a bound on the size of the strategy.
Well,
Upper bound. This would give you an upper bound on the side of the strategy from this. And then you'll be able to command later with your bounded strategy power to try to find this kind of a smaller strategy up to that bound.
okay, so Moshe's comment is that if we have such a heuristic approach, then of course that gives us, well, one upper bound on the number of states that we need to consider in an optimal solution. Of course, I don't have to explore non-determinism for that. Any solution will do, even the deterministically chosen solution. Right? But indeed, later on when we talk about the bounded synthesis problem, there is the obvious question: where do we start? I mean, how do we know where to start searching for the optimal solution? And one reason why these algorithms are still useful, even if you go to this setting, is that the problem, if there exists a solution at all, of course, needs this comprehensive type of solution where we're sure that we don't miss an arbitrarily large winning strategy if it exists, right? Okay. So I wanted to say that parity games have memoryless winning strategies, so therefore they, in a sense, are the conceptually simplest games that do the job we need for synthesis. So now player 0 wins a play if the highest color that is seen infinitely often is even. So here you see that the states are annotated with these numbers, the colors, and now you can try to figure out where the winning region is. Seeing that for parity games is a little bit more tricky than for Büchi games. So here, the winning region for player 0 is this area. Why is that? So it could be that we cycle between V6 and V7, right? So I would, from V7, play back to V6. Then the player 1 plays back to V7, and we stay in this cycle forever. And then we have color 1 and color 2 occurring infinitely often. Well, the highest one between the two is color 2. Therefore, I win the play. Now, from V3, I would also play down to V6, and from there, the play would cycle between V6 and V7. So here we have color 3, color 2, color 1, but of course, this color 3 does not hurt because it only occurs once. So the set of colors that actually occur infinitely often is again 1 and 2, and therefore, if I start from here and then cycle here, I still win the game. Now, if I'm up here, then I can choose to either play from V1 to V0 or to V2. So if I happen to choose V0, then we have color 0 and color 1 occur infinitely often. Therefore, the highest color that occurs infinitely often is 1. I lose the game. If I play to V2, then what will happen is that player 1 actually plays down to V5, and then we return to V1. So now the colors are 1, 2, 3, and if I stay in this cycle infinitely often, then again I lose because the highest color that occurs infinitely often is 3. Now, what makes this sort of fascinating is that it's my choice how I want to lose the game, right? I can play like this and lose with color 1, or I can play like this and lose with color 3, or of course I can alternate between doing the two things, in which case I also lose via color 3. Okay, and then again here we have V4 that looks so promising because it has a high color that is even, but unfortunately player 1 will move me out of here immediately, which means that I'll actually only see this color 4 once, and from then on it's in one of the two losing situations. So, how much time do I have, Moshe? Enough to explain McNaughton?
Enough to explain what?
McNaughton's algorithm.
No.
So then let me just say that tomorrow we'll look at the classic algorithm for parity games, which is McNaughton's algorithm. And this is a recursive solution to the problem, which eliminates in each step at least one state from the game, and then has a new game which is solved recursively. So the nice feature of McNaughton's algorithm is that it's very very simple to understand, and it's an obvious solution to the problem. The disadvantage is that it's also obviously exponential, because you only make, I mean, the progress guarantee that you make is very small. At most, at least the guarantee you have is that you eliminate one state, but not necessarily more. So what I'll do tomorrow is explain that algorithm. There are better algorithms. We saw some of them yesterday already. And of course, there are the exciting new algorithms that came out this year, which solve parity games in quasi-polynomial time. Okay, but more about this tomorrow then.
Thank you.
Thank you.